So you probably don't even notice this, but when I get my face really close to my monitors, these new monitors just like completely wash out my face. Anyways. Okay, we're looking here at the 12.2 problem from practice 4. And this is a centripetal force problem, so a inward acting circular force problem. And if you're unaware, if you don't live kind of where I teach, there's a Chick-fil-A, and this road by Chick-fil-A has got these like kind of rolls to it, and if you're going just fast enough, you can get this like woo feeling going on. So let's pretend that you are going over this hill, and it has a circular arc like this. Okay, we're going over the hill, so there's the circular arc, and here's our car. This circular arc has some radius. We're actually going to put this radius off to the side, or else it'll look dumb. It's got a radius of 40 meters. Let's just pretend. And the car with us inside of it has a mass of 700 kilograms. So it's got a mass of 700 kilograms, which means if it has a weight acting down, remember weight is equal to a mass times gravity, that's 700 times a 9.8. So 700 times 9.8 gives us a weight of 6860 newtons. Now, this car also has another force acting on it. It has a normal force pushing back up on it. Okay, so that's the normal force. Now, the problem is asking us here, how fast would we have to be traveling to feel weightless? That is, the normal force equals 0, because at that point you don't have anything pushing back up on you, you feel nothing. Now, we know the answer here is 19.8 meters per second. Let's see how we get this answer. So we start this by recognizing that this is just a force problem. And when we're looking at force problems, we know that the sum of the forces is going to equal a mass multiplied by an acceleration. That's F equals ma. And in our case here, what we're actually going to be able to say is that the sum of our forces are going to cause a centripetal acceleration. And it's a centripetal acceleration because we're looking at a circular motion here. Even though we're on the outside of the circle, we still have this circular path. Now, one of the first things we need to do is to choose a positive and a negative direction. And we are always going to choose going inward towards the center of our circle is positive. This will allow all of our centripetal accelerations to be positive. And that means going out or away from the circle is going to be negative. So we've got two forces here, a weight, which is positive, and a normal, which is negative. So when we go ahead and sum them together, we can say that the positive weight minus the normal is going to equal a mass times a centripetal acceleration. And we actually know that a centripetal acceleration is equal to v squared over r. That's one of our things we know about centripetal acceleration there. So, whoop, there it is. Now, just given what we have in the problem, we know a bunch of different things here. We know the weight is what we solved for right here, 6860. So we can say the weight here is 6860 newtons minus the normal force, and if we're weightless here, that normal is going to be 0 newtons. That has to equal the mass of us in the car, which we had from the problem was 700 kilograms, multiplied by a velocity squared, which we don't know, so actually what we're looking for, how fast do we have to travel, divided by the radius of our circle we're going through. And in this case, that's 40 meters. And that's it. That's the entire problem set up. We just have to go now and solve for that velocity. To do this, we're going to have to divide each side by the 700 kilograms. And then we're going to have to multiply each side by the 40 meters. That'll do that. That'll do that. So I'm going to have to put a 40 meters over here. Because I'm subtracting 0, that's not going to do anything. So if I rewrote this, it would look something like 40 meters times 6860 newtons all over 700 kilograms. And that's going to equal v squared. And if I need to get rid of that square, I'll take the square root of both sides. The square root gets rid of that square, and that gives us our velocity. And what we should see here is, let's see, 40 times 6860 divided by 700. Take the square root of that. 19.79898987. Okay, 19.8. So we get our 19.8, and it's a speed, so that's meters per second. So, woo! Way to go us. Now for part B to the problem, if we're traveling this speed, but it wasn't a hill that we're going over, it was a dip in the road, how heavy would we feel? And our answer is twice as heavy, or 1370 newtons. So let's talk about that. So this time we've got this hill as a dip. It still has a radius of 40 meters. But this time with our car, our weight is on the outside. That's our 6860. And the normal force is acting upwards or into the circle. So that's a positive, that's a negative. If we go ahead and kind of write this out, this is once again the sum of the forces equals a centripetal acceleration. What we're going to have this time is that the normal force minus the weight, so minus the weight of, here, we'll just write this. We'll just write the weight here, and we know weight is mg, right? So this is just the weight, that's mg. This has to equal to the mass times the centripetal acceleration, v squared over r. Now the reason why I kind of wrote it like this momentarily is I'm going to add the mg term over to the other side. So I can just solve for the normal force, or how heavy you would feel. So your normal force now equals, and if we look at the other side, we're going to have mv squared over r plus mg. And I'm going to note that there's an m in both of these terms, so I'm actually going to pull that m out. I'm going to factor it out, just like this. And what we see now is that what we feel is our weight is just going to be mass multiplied by some new acceleration term. Both of these are accelerations, so they can be added together, and a mass multiplied by an acceleration will give us a force. Our acceleration we're going to feel is just gravity plus this extra centripetal acceleration. And if we take our speed from before, 19.8, and we square it, and then divide it by that radius of the loop, or rather the dip, 40, we get this value right here as 9.8. So 9.8 is the value of g, so this could be thought of as just g plus g, or 2 times gravity, which means you're going to feel twice as heavy. If we wanted to write it out completely, we could just say that this is going to be 700 times the quantity of 19.8 squared over 40 plus 9.8. In the end there, this just gives you 9.8 plus 9.8, which is 19.8, which is twice of gravity. And we do see that our final answer here will be essentially 700 times 2g, which is going to be our 13,720 newtons. And that's why you feel twice as heavy there. Okay, so this is just one way to think about this. As we saw in the notes, if you had a hill like our last problem, we actually have the same equation here, but that plus would just become a minus. Or rather, it would be rewritten. It'd be written like this. It'd be written as g minus v squared over r. So that's how you could write it in the previous problem. We could write it with the plus sign here the way we did it. So that's just a quick little example of some centripetal forces. Nothing too crazy, but it is important to keep in mind that whenever we're setting this problem up, going inward to our circle is positive. Going outward is negative, as we saw in both problems here. And then just really setting up sum of forces equals ma, where our acceleration is now centripetal acceleration, which is v squared over r. So with that, this problem is finished. So take it easy, everybody. Adios. I'll put the fin right here. Have a good one.